Welcome to ECEN 215 Principles of Electrical Engineering. Today we're going to discuss AC equivalent circuits. So previously we had DC equivalent circuits when we were going over purely resistive elements and looking at DC circuit analysis. The models, the Thevenin equivalent and also the Norton equivalent that we'll discuss in a moment, nothing really has changed in the sense of the concept behind it. Of course, the thing that's changed now is we have brought in the concept of AC phasors and AC power supplies. So we have a frequency component. We have actual impedances now instead of resistances. So it's just the mathematics has changed, but the overall model has stayed the same. So again, V of T is equal to the open circuit voltage. So the same principles that we learn haven't changed. And that Z of T is equal to the open circuit voltage over the short circuit voltage or short circuit current of the circuit given the load. So everything that you learned in doing the Thevenin equivalents and Norton equivalents in the DC resistive analysis still applies. It's just now we have complex impedances involved. I would emphasize, if you are still confused on how to do a DC Thevenin equivalent model, I would actually go back, review the lecture on that, review the homework, talk with me or a TA or someone else, and get some help on how to master doing the DC Thevenin equivalent, Norton equivalents first before continuing on. Because the only real difference here is that the mathematics get more complex because now we're introducing phasors and you're having to keep up with the complex impedances and things like that. And there's also, just as a fair warning, there's going to be again another conjugate event as well, another discussion of the complex conjugate. So instead of getting confused by all the additional new mathematics, I would make sure you're comfortable in doing the DC resistive versions first before continuing on with this. Because if you have that, then this is fairly straightforward. So just to confirm everything here, the Thevenin impedance ZT can be found by, again, using the zeroing method. And that is where we zero out the independent sources. That means that if you have a voltage supply, zeroing it out means it becomes a short. So if we had an actual circuit here instead of the Thevenin, the power supply would be a short. If it was a current supply, it becomes an open. So that model still works. It works completely well. It just now, instead of computing the equivalent resistance of the circuit once you've done the zeroing, you would now do the Thevenin or the equivalent impedance. So ZEQ instead of REQ. So everything stays exactly the same process. So if you were really good at doing the Thevenin or the resistance equivalent to get the Thevenin circuit resistance, RTH, then this will work just as well using the same process. Again, when you zero independent sources, voltages become shorts and the currents become an open. They just leave the circuit. And then you just end up with just a circuit full of impedances. And again, if you have a power supply that has become shorted in the case of a voltage source, the equivalent impedance of that, by the way, is a 0 ohm resistor. So, you know, there was some confusions on some of the tests and on some of the homework, like, well, once I short it out, what happens to all the other components down circuit that are also in parallel with the voltage supply? Well, that voltage supply is shorted. All those other sources are now in parallel with a 0 ohm resistor effectively. So there's 0 ohms. They're now wires. Now, if you have a dependent source, you can't use this method. You have to continue to use the first find the open circuit voltage and then apply a resistor of 0 ohms, basically apply a short across the load of the circuit you're converting over, and then you get the short circuit current through that leg, and that becomes your ISC, and then ZT is just an open circuit over the ISC current. The Norton equivalent model is the same, except the only difference is now the Norton current is just equal to ZT, which is just VOC over ZT, which also happens to be equal to the short circuit current. So let's do a simple example here. Like I said, the model that we've learned hasn't changed since the DC circuit analysis. The only thing we're doing now is we got complex impedances and an AC power supply. So here we have VS, it's 100 volts, phase angle 0 degrees. We got a 100 ohm resistor. We got a capacitor that's once converted over to a complex impedance is minus J100 ohms. And then we have this current source that's also sinusoid that is 1 volt at 90 degrees. So all this are sinusoidal devices. We just have converted them over into their phasor form. And now we're asking to get the circuit model at the terminals A and B. So to do that, for this circuit here, we're going to do nodal analysis. And we're going to start by finding a reference node, which we'll set this as the reference node, and we're going to call this node 1. And all we need to do, since we want VAB, which is the open circuit voltage, all I need to do, since this is my reference node, is solve for V1, and I'll have my open circuit voltage. So let me write an equation for V1. So V1 minus Vs over 100 ohms. So the current that is going here, let me draw on the screen here so that we can follow along. So we need the current that is going from this node, and again, this is all the same node. So we're looking for the current that is going, leaving V1. That's how I write my equations, leaving V1 and going this way, which that is simply V1, this current here, or this voltage here, minus the voltages at this terminal here, which is Vs. So V1 minus Vs over 100 ohms. So that's current number 1 that we have that's going this way. So we have that. And then we need the current that's going through this capacitor here, which that simply is V1 over minus J100. So that is this current here. So that's current number 2. Current number 3 is the current that is going from V1 to V0 through this leg. Well, we're told what that is. That's IS. And it is going in the direction that we want. So I defined it as going from V1 to V0, and that just so happens to be how the current is given. If this, for instance, was not this, but instead was in this direction, then we would put a negative sign in front of it. But in this case, we were given IS is going in that direction. So using that, we now have this equation, and we just need to solve for V1 now. So let's actually stick in the actual values for Vs and Is, and we end up with this, and we just now need to solve for V1. V1 is equal to the open circuit voltage, which is also known as Vt. As soon as we have the open circuit voltage, we know what Vt is. If you go through the math on that and you do the algebra, you end up with V1 equals to 100 minus 90 degrees. So now that we have VT, we now need to solve for ZT. So again, there's no order to the steps. There's just 2 steps really for the Thevenin equivalent. You can solve for ZT first and then come back and solve for VT. It doesn't matter which order you do it. I usually do open circuit voltage first and then come back and do ZT. And the method I'm using here is the zeroing method. If you prefer doing the short circuit current method, which is correct, especially if there's dependent sources, then please do so. Whatever method works for you. I find it myself easier to do the zeroing method when it has a bunch of independent sources, which we have 2 of them in this case. Just a reminder, and for the zeroing principle and method, is if you have a voltage source, it becomes a short, and if it's a current source, it is an open. It's as simple as that. In that case, we had 2 independent sources. We had a current source and we had a voltage source. So we had a voltage source that was located right here, and it became a short. And we also had a current source that was located right here, and it became an open. So we ended up with just 2 components, a capacitor and a resistor, that are now in parallel because the voltage source became a short. So we have 100 in parallel, 100 ohm resistor in parallel with the minus J100 ohm capacitor. And so this method uses the 1 over the reciprocal method. You could also use the Z1 times Z2 over Z1 plus Z2. You get to the same value. By doing this, you end up getting to ZT equal to 70.71 with a phase angle of minus 45 degrees, or 50 minus J50 ohms. So that is ZT. So now we have VT and we have ZT. We're done. We have everything we need to come up with the model, which is simply this. VT is 100 phase angle minus 90 degrees, and ZT is 50 minus 50 J ohms. So now we need to talk about the maximum average power transfer. Now, when we covered DC equivalent circuits and we were looking at the Thevenin model then, or the Norton model, and we had to come up with what was the maximum, what was the load resistor that we could attach to the circuit to achieve the maximum average power transfer. And we did that, and we turned it RL was equal to RT. Now we have a Thevenin equivalent. Now we have a circuit that has VT and ZT into it. And so the natural instinct would be, what is Z load? And so naturally, when you first look at this, your answer is, well, obviously Z load must be equal to ZT because RL was equal to RT, so therefore by contrast and compare, it's probably the same thing. It's close. It just so happens, remember when we were talking about power in the previous topic, that power is related to, complex power is related to V times I conjugate. Well, because of that conjugate, because of that phase angle difference between voltage and power, we have to take that into account here. So you actually transfer the maximum average power transfer on an AC circuit equivalent when Z load happens to be equal to the complex conjugate of ZT. So I won't go through the math on this. I mean, you can go back to the previous lecture topic on power, and you can see that this is true. But the maximum hour power transfer for Z load is when it is equal to ZT conjugate. And just as a refresher, conjugate is just where you're flipping the imaginary term. So if you have the load was 5 plus 6J ohms, then the conjugate would be equal to minus 6J ohms. So it's the same real resistance. It's just you're flipping the imaginary component. And also just flip the imaginary, the phase angle as well. If it was 5 with a phase angle of 10 degrees was ZT, then Z load would be 5 phase angle of minus 10 degrees. So you're just flipping the imaginary component, flipping the angle. So just taking this one and turning it into this one. So it just has to do with the imaginary component. And so that's all you need to know for finding the load to match that. So let's go ahead and take a look at some examples of this. So here we have V of t equal to 100 minus 90 degrees with ZT equal 50 minus J50 50 ohms. This is what we just came up with earlier in the previous example. This was our Thevenin model. And so the question is, what is the optimized load here to put on these terminals that would give us the maximum average power transfer? And that is where Z load, instead of being equal to 50 minus J50, we now go 50 plus J50. We took the conjugate. So that's the key difference. And that's all you have to do. This is the maximum average power transfer. Now, what if we wanted to put a purely resistive load here? So previously we had, in the previous slide, we put, 50 plus J50 ohms out here. We put a complex load. But sometimes you don't want to create a purely complex load. Sometimes you just want to put a resistor out there, like a heater or something that just is 100% resistive. What can you do there? Where there you want to come up with the magnitude that matches that. So that occurs. So the maximum average power transfer, maximum average power transfer with only a resistive load occurs when that load, R load, is equal to the magnitude of ZT. Again, magnitude. So we have 50 minus J50. So if we take the magnitude of that, which would be 50 squared plus 50 squared, and we take the square root of that, we end up with 70.71 ohms. And that's what we get here. So if I put a resistor out here, I will get the maximum average power transfer using a resistor only. No capacitor, no inductor, just purely resistive when I have the R load equal to 70.71. So in summary, we looked at using Thevenin and Norton equivalent circuits in AC circuit analysis. So again, we're just projecting forward what we did in the DC analysis now into the AC analysis. Everything more or less stayed exactly the same, except when it really came to the loads. So that's the key difference, was the maximum power transfer. So we have a complex impedance, we have a resistive load. For the complex impedance, you had to take the conjugate of it, and for the resistive load, we just had to take the magnitude of ZT. And that's it. There's not really a lot to it. Again, I like to emphasize that if you are struggling with Thevenin equivalents, Norton equivalents, definitely come please see me in my office hours or talk to a TA. Definitely review the previous lectures on these topics. Thevenin and Nortons do seem to cause struggling because it is a lot of circuit analysis to figure out all the values. But once you've mastered the DC part, doing the AC part is just doing it with phasors. So that's the key difference. It's just a mathematical upgrade, if you will, to the complexity of the project or problem. Alrighty, so again, definitely would recommend coming to the Q&A so we can discuss this and work a few more problems and address any questions that you may have.